Hi everyone. This is the second half of the implicit differentiation lesson. We're going to pick up here with examples 4 and 5. Example 4 is very similar to what you've already seen. Example 5 gets into how to do a second derivative, which adds an extra layer of fun to this. So let's take a second and talk about these. So let's start out with the very first bullet point here is just find dy dx. So that's a very straightforward thing. We've done this lots of times. So I'm going to buzz through and find my derivatives of all of my pieces. So I'm doing a derivative of 2y, which your brain should be screaming 2, right? But also we're taking a derivative of y, so we need to start with a dy dx times 2. Okay? Equals derivative of x squared, which is 2x, and that can just be a 2x, plus, now I'm about to take a derivative of sine y, so I'm going to throw a dy dx in there. And then multiplied by derivative of sine, which is cosine. So I'm going to say this is cosine y. Okay. We need to get the dy dx's together, and in order to do that, they have to be on the same side of the equation. So I'm going to pick up this dy dx term with the cosine y and slide it over here. And when I do that, and if this confuses you, come approach me in class and I'll talk you through it. But I'm going to slide it over here, and I'm also going to pull out the dy dx at the same time. So I'm going to say dy dx, and then I'm going to have 2 minus cosine y. Because the left side would say dy dx 2 minus dy dx cosine y, and then I'm pulling the dy dx out in front, so I have 2 minus cosine y. Over here on the right side, what I have left is just a 2x. And then to get dy dx alone, I'm going to divide by this parenthesis. So what I end up with is dy dx equals 2x divided by 2 minus cosine y. Okay, that's my derivative. That's my answer. Okay. The next question says, is there any place where the slope of the tangent line is undefined? If so, identify where. If not, explain why not. Okay, so this represents slope of my tangent line, and what I want to know is there any way for this thing to be undefined? Okay, well, undefined typically means we've got a denominator equal to 0, right? So that's what I want to be asking myself is, can I make this 2 minus cosine y equal to 0? Well, if 2 minus cosine y equals 0, if I move the cosine y to the other side, what I would end up with is 2 is equal to cosine y. And so can we get an answer for that? Is there a y value that where if I took a cosine it would equal 2? Because if there is, that's going to cause me trouble. And I hope your brain is telling you the answer right now. Okay? I hope that you're looking at that and you already know. But let me show you what you would do if you weren't sure. This is a situation where I'm solving for an angle measure, right? So I'm going to do an inverse cosine of 2 to find out what angle would have a cosine of 2. And I get a domain error, okay? The reason for that is you can't have a cosine of 2, right? When you think about like your unit circle, there's no such thing as a cosine of 2. The biggest cosine you can ever have is 1, all right? Cosine is limited between 1 and -1, so we're never going to have a cosine equal to 2, okay? So this is not possible, which means that pretty much answers my question that there is no place where I would have an undefined tangent line, okay? Now, if this could be done, then whatever y value I found here at that location, I would have a undefined tangent value, okay? But as it stands, I can't make that happen, and so there is no such thing as an undefined tangent with this particular problem. Okay, let's look at a second derivative. And we can't look at a second derivative until we find a first derivative, so let's do that. In fact, you might want to pause the video and try that part on your own, because finding the first derivative is what we've been doing this whole time, right? But my first derivative, I'm going to say this is a 6x squared minus, I'm taking a derivative of something with a y, so dy dx times 6y, and then derivative of 8 is 0. Okay, I'm going to move the dy dx term to the other side so that I can isolate it. So I have 6x squared equals dy dx times 6y, because I added it to the other side. Now I'm going to divide by the 6y to get dy dx alone. So I have 6x squared divided by 6y equals dy dx. And this is a situation where I would probably get rid of these 6's and just say that dy dx is really x squared over y. Okay, perfect. That's not so bad. Now I have to find the second derivative. Well, the second derivative is the derivative of this. It's the derivative of the derivative, right? So now I'm taking a derivative of this x squared over y. And that is going to require some quotient rule, okay? So my u is x squared. My v is y. So my u prime is 2x. And my v prime is dy dx. So let's set up quotient rule. My second derivative, because that's what I'm doing, right, is I took a derivative of both sides. So this is dx squared. Okay, u prime v, so that's 2xy, minus v prime u, so that's dy dx times x squared. And that whole thing is over my denominator, which is y squared. Okay, normally this is where we would dive in and start trying to get dy dx by itself. But here's the thing. We're not trying to find dy dx. We're trying to find this. And that's what we have. Okay? But we can't just leave this dy dx in the middle of the problem. Like, what's the deal with that? So here's what this one requires you to do. We know what dy dx is. Do you see this statement right here? Dy dx is x squared over y. So what I'm going to do is I'm going to take this x squared over y and I'm going to substitute it right in for that dy dx, because that's what it's equal to, right? So I'm going to rewrite this thing, and you can decide how much simplifying you want to do. Sometimes you might need to do more than others. So 2xy minus, and in place of dy dx, I'm going to say x squared over y times x squared. And all of that is over y squared. So that's it. That's your second derivative. That's your answer. There probably are some things here that we could maybe simplify. Trying to decide how much of that I want to do. Yeah, I don't think we would have to worry about it. I think we could just leave it here. Little things like, could we make this x to the 4th power? Sure. Could we split it up and divide both sides by y squared? We could. Okay, but really what I want you to know, the biggest, most important part of this is just that when you have this dy dx in a second derivative, because you already have found the second derivative, you have to replace it with what you already found for dy dx. So just take that thing and plop it in there and you're good to go. Okay? Okay, I think that's it for implicit differentiation. This, I know it looks complicated, but the more you practice this, I promise the better you're going to get at it. This is not even going to feel hard by a week from now. Okay? So keep at it. We'll practice lots together in class. Ask lots of questions if you're confused on things. And yeah, I'll see you soon.